All right, thank you so much. So welcome everyone to today's session, Auto-Trained Time Series Forecast Model with AML and ADB. My name is Mort Steller or Mo Steller, both is fine for me. I will go through the presentation within, I would say, the next 20 minutes, and then we have 2 demos planned and that we are going to step through. And we will handle questions in between. I'll give some time to ask questions in case somebody has a question. I'll try to monitor the chat and the questions on the side. If not, we'll take them at the end. So everybody has time to ask questions, and I'll leave enough time by the end, basically, to go through those questions. So a little bit about myself. So most are part of Microsoft, the worldwide commercial business unit, and particularly responsible for AIML. My team is building with customers worldwide AI solutions and helps basically accounts to move to production with those AIML solutions. We are cross-area, cross-industry, so really anything under the sun that comes to us, we work with. And as there's such a large need for AIML in the field for innovation to solve particular business problems, we are basically very busy and working on all these very specific problems. Again, as I mentioned, cross-industry. My focus area within the team are, from a technical perspective, on NLP, deep learning time series. That's sort of like my main go-to field. I'm not a computer vision person by any means, so everybody has sort of like their own fields of expertise. And I'm also very interested in any type of scalable AI. So how can you really build really large engines? So the topic of MLOps, AIOps comes into play there. And of course, responsible AI and ethics are top of mind for anybody within my team, but also of myself when working with customers together. Focus industries, what I've done or the work I've done in the last years are very healthcare related, or HLS related in general, also insurance, finance, supply chain. So those are usually my go-to industries where I know the data very well that is dealt with in these industries, and hence you'll find a lot of involvement of myself within that area. Hence, you can imagine the topic of today, time series, is relatively close related to those type of industries on a worldwide basis. So that's enough about me. I really want to get to the topic here, since this is why everyone is here. So today, this is the agenda. We are going to talk a little bit about time series forecasting in general. Expect this to be a level 200 to 300 sessions. So it's not going to be overly complex. We will not talk about model architectures. It's going to be a little bit more on the solutioning side. So you will see how to build this type of end-to-end solutions with the technologies that are suggested here. We will have a quick product preview. So what basically recently came out in Azure Machine Learning that may be helpful for your own development. We will talk a little bit about advanced parameters when basically setting up a end-to-end pipeline to run a forecasting model for your end-to-end engine. And we will talk about the better together architecture, we'll call it. So basically a combined architecture of Azure Databricks and Azure Machine Learning, how this looks like. And then based on that architecture, we will run a demo. I actually have prepared 2 demos for you all. One demo is going to be a univariate time series example. So it's going to be relatively simplistic, but it gets the idea across what the basic building blocks are needed to build this end-to-end engine. And then we'll look at a little bit more sophisticated example that will show you a many models use case, how to really scale your time series use cases into the thousands, essentially, in case you're have a use case that goes into this particular direction. All right, let's step right in. First topic, time series forecasting. So this is going to be a little bit of an introduction. You may be aware of a lot of these topics, and what type of time series are we dealing with usually when working on such ML problems? So usually we have 3 cases. We have one is the univariate time series use case. So this is usually when you have a column that is a time particular column or time focused column and a target column. where you basically build often statistical models on short series of, or if you have more sophisticated series, you can use other types of algorithms, but it focuses usually on these two columns. You can build lags into these columns as well within your prediction, but from a use case perspective, this is really what the univariate time series is. The multivariate is just a set of sub-time series or sub-series within your data set, or you have multiple columns basically that have other features that inform the time series and your target variable for your prediction, essentially. And we have the use case of DNNs, which are the deep learning scenario, which you usually can use in either or scenario in the univariate or multivariate, but it's a little bit out of the box as it uses different types of architectures and not the very traditional methods, as you may be aware of, to do any type of forecasting. And this is going to be the same in pretty much any type of open source library you use. They will offer basically these type of options for you. Or if you use an enterprise tool, basically, that is in the marketplace. And at Microsoft, we're doing it pretty much the same way. So if you look at Azure Machine Learning, we deal with, in classical machine learning, we deal with three large fields. So basically, we look at progression, time series forecasting or forecasting, and classification. And there is a model suite that is given to you that enables your AutoML runs. So if you think about, I don't know, 7 years back at this point, where data scientists had their like top 5 algorithms and they built model after model essentially, which took a lot of time. With AutoML, the time to product got shortened. So that's the entire value proposition of AutoML. And now you get a suite of models that you can run against your target variable and your data set to really build models in a scaled fast fashion. And for time series in particular, which is the topic of today, we'll focus basically on the center box here, where you have standard algorithms that you're using for time series prediction. And in particular, also a couple of open source libraries that were built in. So Prophet, developed by Meta, for example, is one library that is going to be part of that stack within forecasting AutoML. But also the DNN solution I mentioned in one of the prior slides would focus on the forecast TCN model, which is the DNN architecture that Microsoft is giving you essentially when doing time series forecasting. And there are different iterations. Basically, there's a team that is working particularly on this particular algorithm, so it evolves by architecture and it will be then made available for you, so you can basically run it on your end. You need to enable it within a parameter. We'll see this in a second here, but just for your awareness, it is basically built in the stack. There's often this question, can we run deep learning basically on time series? And people get really excited, and it's very like evangelized on social media. Deep learning, you read it everywhere. But just be aware of sometimes traditional algorithms, especially on short series, can, with less data, can exceed those deep learning algorithms. It really comes down to how much data do you have, and in the end, it comes down to your accuracy metric. What is more sufficient, essentially, for your univariate or multivariate time series? Right, fair enough. This is the general intro to the algorithm suite we are looking at here within this session. I now want to give you a little bit of a sneak peek how this is going to look like in Azure Machine Learning. And in Azure Machine Learning, we're dedicated to develop the product ongoingly in different types of versions, and with different types of versions, there are new features getting introduced. And I just want to show you a couple of features that recently got introduced that are helpful for you for your time series forecast engine you're going to build within your company or within your personal project or wherever you're going to use that capability. I want to focus on 4 particularly here. The first one is a solution accelerator that Microsoft developed and put into the marketplace. So think about it this way. Solutions accelerators are services plays, so different types of Azure services that come together and enable for you a particular solution. So this is like the general definition. And here in this example, specifically to time series forecasting, we offer now 2 solution accelerators. One is the many model solution accelerator. We'll see a demo about that in a second, and the hierarchical time series solution accelerator. So both tackle different problems and basically solve a problem for you in a decreased amount of time. So let me explain what that means. So for many models, for the many model solution accelerator, you deal with the business problem to use this solution accelerator that requires to scale out time series models by n, so by a factor of n essentially. If you have a data set that has, let's say, particular stores, because you work in retail and you want to make a prediction on the store level, or you work in the restaurant business and you want to make a prediction on your large grocery chain restaurants, essentially based on sales. You'll sort of have a implied hierarchy within your data set. And because you don't want to build a model over and over and over again for your tens of thousands of stores, you can use the many model solution accelerator, and it basically enables a scale and repeatability to build a model under AutoML here in this example, n times as many sub-entities you have. So it basically scales out on a large scale your use case, and your basically time to product is even faster. With a hierarchical time series solution accelerator, it is sort of similar, but approaches a little bit of a different problem. So here we are looking at a data set that is highly hierarchical. So think about, you have a geolocation, you have a county location, you have a city location, and it breaks down the entire data set step by step, essentially. That's when that accelerator comes into play and then runs basically time series models within the lowest entity or the entity you're basically defining. I want to go to the next point that is in public preview. So the test set ingestion. You may think this is very like general, as you split your data set into train, validation, and test, as in most classical ML use cases. Now, Microsoft made it possible that we now have a test set parameter within your AutoML config. So the AutoML config is basically the overarching parameter where you have your hyperparameters listed essentially, and now there is one that is called test set where you can align your data set to it. Before, you only had the train and validation, and you had basically to run your test step outside of that. Now it's basically built in, so it saves you basically code writing and makes the overall pipeline more concise. So this is really good, and it's just more neat for the development for any type of AI practitioner. The next item, we're going to see an example about this also here on the slide in a second, is the code generation. So this is really cool, actually. So often, if you look into the general AutoML marketplace, these AutoML models tend to be black box models, even though they are considered to be classical machine learning, which can be made explainable, but you will never see the code base underneath. So with the code generation, on one click within your UI, you actually can export the code of the model that you're selecting. So if you have a particular model that you see within your AutoML leaderboard as the leading model, you can select it and say export, so to speak, and you get the code base. And it really helps you if you think from a data science lifecycle perspective, how you develop, meaning first you build a baseline model, maybe based on AutoML. Your second iteration is going to be a more customized trained model where you have, I don't know, hyperparameter searches, or you run some type of neural architecture search on your algorithms to find an even better model based on the leading model of the AutoML leaderboard. Then the code generation really comes into play, because you can extract the code and you can easily implement those type of searches within the code base without having to redevelop the leading model that was given to you as the baseline model for your product version 0.1 or whatnot. So it's a really neat feature, and I was waiting for it myself for a while, so I'm happy to show this in a second here, how this looks like. And lastly, the model explainability got extended and is now generally available to AutoML. So this is really about a model explainability, essentially, that you can unpack your model and you can show basically your business leaders how your model fundamentally works underneath, and if there are any bias implications or other type of explainable features that need to be communicated to your organization. Next, let's dive a little bit into the code generation. So what I just mentioned to you all. So this is, I guess, my personal pick here from that prior list as the most exciting feature. So what's going to happen is with the code generation, you basically run your individual models based on AutoML, right? So you can do this through the SDK or through the UI. This is absolutely your choice. And you'll get basically your answer in a leaderboard. That leaderboard you can export, again, within code, or you can look at it within the UI. And within that leaderboard, you can say, I want model 1, 2, 3, or model 1, let's say. And because it's your favorite model, based on runtime, based on compute intensity, based on accuracy metric, whatever it is, and now you want to export that. And it really gives you that code transparency and the full control over your code that you can then move back, let's say, into a GitHub repository, enable a full DevOps type of process around it, to have this full control over your code base, and then essentially develop your next gen model, which should be beyond that baseline you have created with AutoML in the first place. And how this is going to look like, took a couple of screenshots here. You see here on the left side currently, you see basically a AutoML run. Disregard the AOC metric here. I know this is a quotation marks not so good result, but it's just to showcase essentially the functionality here. So within this example, you see that the XGBoost classifier got selected as the model that we want to code generate. And you see basically, after clicking on a view generated code on the right side, a script, in this case, a script.py file that shows you the model that has been trained and that has achieved that metric. So, and it's, there's no secret around it, right? It's a scikit-learn model in that case. And the awesomeness about this is now that you can take this code base, and as I mentioned before, you can replace those hyperparameters that you see listed within the center of the right side under XGBoost classifier. And you can, for example, enable for your next model, as I mentioned, search spaces in whatever type of search method you choose, basically, to find even a better model that maybe AutoML has not found for you. And I think this is really neat in case you select a DNN and you want to do a neural architecture search on it. So basically search on large parameter spaces or vector spaces, the best DNN, essentially, rather the DNN that AutoML had suggested to you. So it's a really neat capability that is highly recommended to try out and sign up basically through AML, and it really helps you to gain more insights within your code base. Within AML, within these individual runs, when you build these forecasting models, there are a couple of hyperparameters I want to bring your attention to, especially in the use case of connecting it to Azure Databricks. And a couple of these hyperparameters I have listed here. Those are just a few. There are others that may be important. This is my, let's see, top 7 in that use case. And they will help you basically to build sufficiently a model. So, and also make certain decisions on your model training. So you can see the two voting, the two ensemble options you have. So the stacked ensemble and the voting ensemble, you can enable them if you want. Usually those type of merge models or ensemble models in this case, usually achieve a better accuracy based on the accuracy metrics, and they're always the leading models. If you select that model in the end, is a discussion point within your team because you know, they appear a little bit black boxy usually, and you want to rather select a very clean algorithm, so it's not an ensemble model. That's my personal recommendation, or when I talk to customers, especially for the first model development, this may be the better choice. But if you're comfortable using ensemble models, using or enabling these parameters are very helpful to basically get them within your AutoML run. Enable the Onyx capability is really neat. So in case you decide to pack up your model as an Onyx model later on to run inference calls on it, or if you have, for example, a Synapse instance in Azure, it comes really it's really helping you to basically convert the model into Onyx, move it into Synapse, and then, for example, have a T-SQL function running on your Onyx model to enable data engineers to also run inference calls. Or in general, if you want to run an Onyx inference and this just fits more your overall MLOps type of system, it is recommended to look into this particular parameter. The Spark context is important if you want to run actually your AML on a Spark cluster, so you need to reference that rather on the compute that comes in AML. So this is more for ADB. I think I just said AML, I meant ADB. Apologies for that. The featureization is important in case you want to pre-process basically your features in a different type of manner that can be custom, from a custom perspective, defined for you. Early stopping to basically select your stopping ranges. This is a relatively standard parameter, but considerable important for your AutoML run. And then if you want to apply basically seasonality, so if you do your EDA type step essentially before running your time series model and you detect seasonality, you can specifically say enable or set seasonality within your time series. From a compute perspective, we got to consider two things here. So where do you want to run essentially your model? You have really two choices. You can run it in ADB on any type of cluster, a 7x and higher, or you can choose basically the diverse options of compute within AML and reference your compute cluster there, which is my personal recommendation in this particular use case here, because as larger the data is, you can really select on your end, am I going to go with a standard compute, if I'm going to go with an advanced compute that uses the scalability of the nodes in the clusters, especially in a many model use case well, or maybe you require an HPC type of resource because you have a very large data essentially and you want to run a DNN. So this is more diverse essentially for you and also plays better with AML forecasting. So this is the regular stack for your compute. Just keep this in mind. You have different choices. Your best choice is essentially what makes the most sense to your use case and what makes the most sense basically to the overall engine you're going to build, the system essentially for forecasting. So now we're going to get a little bit more technical. That was sort of like the introduction. I want to show you the architecture and then we are going to get to the demo. So we call this better together architecture as basically Azure Databricks and Azure Machine Learning sort of play together here. And it's a fairly common use case as the power of Spark enabled a lot of data engineers essentially to process within the big data era, how it was called, large amounts of data. Hence, Databricks is playing an important role here. Within the architecture, the first step we have to consider is basically our incoming data. This is usually enterprise data that comes in through your many systems you have, whatever these systems are, could be on-prem, could be cloud, could be whatever type of other data sources you have, and considerably third-party data, especially in time series forecasting. If you have a time series use case that is at a particular geolocation and outside factors will influence that time series, but you don't have that data available necessarily within your enterprise data, it should be considered to bring in third-party data to increase your accuracy matrix during your prediction steps. So there is a common use case, for example, if you do some type of event prediction or something like that. Event prediction is influenced by other factors within a city. For example, I live in Austin, Texas. We just had South by Southwest here that usually brings in a lot of cash flow for a lot of businesses. So if you think about from a prediction perspective, maybe time series are going to be off within that time. So bringing in third-party data of travel numbers, or I don't know how the weather is going to be, may influence certain type of sales forecasting. Hence, this is a recommendation and a really important step. Let's look at the next step. So what's going to happen with this data? You have two choices to distribute your data workload. So at number one here, you basically can use Azure Databricks or the Azure Data Factory to distribute the incoming data into different types of staging areas. That could be like a data lake, for example. That could be like Azure Synapse, so a more warehoused type of approach, or you use an Azure SQL DB. Within the Azure Cloud. There are other options available too, but those are the three most common basically to get your data basically from A to B essentially and have it in a set fashion. And we are looking here currently at a batch step that runs. You can certainly enable a near real-time engine at this point as well, but again, it's not the focus of this particular presentation. Next, we are training our model. So we were talking about the play between the two tools, essentially. So you have basically Azure Databricks available where your code base lives, and you reach from Azure Databricks into Azure Machine Learning to utilize the compute and basically train your model. So both play together here, which is relatively important. And now from an inference perspective, let's say your model is trained, you really have two options. You have the batch option and you have the near real-time option. So in a batch option, you would exactly follow that path. You have some delay here to move your data basically from your source to your target systems. And then you basically can trigger your inference in ADB. And those batches are going to be delivered, I don't know, on a schedule that is dependent on your individual business. Or in case you're working in a near real-time scenario, you would then basically have a deployed endpoint using AKS here at number 6, and you can then run basically your inference in near real time. There is an option also to use the near real time for streaming in Databricks as well. I would personally recommend to go with deployed endpoint. This is also the idea Microsoft is moving to, having more of these endpoints, and then you can bring a scalability more in the endpoint itself. And if you think about from a developer's perspective, if you want to move this endpoint to some kind of application or whatnot, this is the more recommended way from my personal perspective for near real time. Looking next at the analytical workload. So let's say you have some type of inference call running. You want to write to another target. You can do this again in any of these three choices. It is fully up to you. Maybe you have a different target system. I think in a batch scenario, it's pretty nice to write it back to Azure Synapse, where you have sort of a data warehouse type of environment, essentially, where your data is going to be stored in a very unified fashion that serves your entire company or your individual subunit within your company. And from the workload, from the analytical workload type of storage, you can then basically visualize and serve your front end. And this can be done in any type of web application or in Power BI, in some type of BI tool, where then business users basically access this tool and gain insights out of the forecast that you're going to visualize or whatnot, whatever their use case is essentially. So this would be the end-to-end architecture. And within the demo in a second, we're looking at this step here in between, so at 3 and 4. This is going to be important for us. Anything else is dependent, again, on your enterprise architecture, whatnot. However this is set up, this is a recommendation and how we see from a Microsoft perspective with ADB and AML forecasting could be enabled. I spoke about the many model use case a second ago. So this particular end-to-end architecture can be done in a univariate and a multivariate way, as shown in the beginning. But I also brought up the solution accelerator we had enabled. So the solution accelerator would then be deployed essentially within the Azure Databricks environment and be executed against Azure ML. And the solution accelerator, because it's a little bit more complex, would look the following. So I display here a little bit of a sub-architecture. You can see how this looks like. You have a couple of example use cases here on the site I'm not going into, but essentially what's going to happen is you have your raw data at one point. This is the first target environment. You read with a tool, so Azure Databricks basically, the data, split it accordingly, and then you kick off a training step in AML, which basically segments within that training pipeline your data set, and it will be executed step by step in mini batches within AML. And again, we'll see this in a second here in the UI. You will then get a individual model per, in this case, store. And it's fully automated for you, basically. You don't have to build model by model or build some funky functions, essentially, that allow you this iteration. It's done within the accelerator. And in the end, you can run inference very easily off that accelerator, because that store ID essentially is going to be tied to the model underneath. I'm trying to simplify this a little bit here. So when the new data comes in, you want to run inference, it's able to tie the right model to your data, and you can run your prediction accordingly. Overall, within this entire system, within this entire architecture, I want to just highlight here within this presentation, we're looking at a play between three types of operations. Data ops, you need to be aware of how your data flows through your systems and ensure governance. ML ops, so in case you have retraining processes or particular trigger functions, basically, that can be time-based, metric-based, or whatever your business is seeking based to retrain your models in a certain cycle. I would recommend for time series, this is like really a best practice, to retrain immediately when you get new data. As you can imagine, from like a forecast perspective, let's say it deviates from your actual incoming data, and as further you predict out, it starts to deviate even more. And so if you bake the data immediately into your training set, the deviation shrinks basically on the short term. So you want to retrain as many times as you can, or as many times your business allows it. I think this is the better way to say it. In my experience, especially when you work in batch loads, it's a little more difficult in your real-time scenarios, but if you work in batch loads, and let's say your batch system delivers once a day, every half day, or maybe once a week, usually a retraining overnight is a good way to do that. So, and then to deliver a new forecast, essentially. And from a DevOps perspective, just tying everything together, essentially the entire end-to-end system to trigger basically particular jobs and whatnot, it comes into play to really automate your data ops and your ML ops processes. All right, now we're going to look at the demo. Within the demo, we're going to go through two use cases. I mentioned that the Univariate time series use case. I'm going to show you those particular time series parameters in the ML config. And then we are going to also run an inference run with a many model time series data. And I'll try to showcase that to you as best as I can within the example within ADB. So let me switch my screen here to my notebook. I believe everybody can see my notebook at this point. And the first use case I'm going to show you is the Univariate time series. So here in this particular use case, we're trying to forecast energy demand, which is a pretty common problem, I would say, within time series forecasting for many companies worldwide. And the main introduction to this notebook here is the boilerplate code I want to show you that you can reuse over and over and over again for any of the time series use cases you're working on. So first, we're using the second to latest version. So there was actually like a version uptick to 1.09.1 a couple of days ago. So I ran this on the 15th, basically about a week ago last time. So hence it's not the newest version, but it shouldn't create a problem here for this example. As I'm not live running this, I'm going to show you the executed portions. We're going to import our library stack, basically. This is fairly common. You are probably very familiar with most of these libraries. And down here for Azure ML, those are the Azure ML.core libraries that basically enable you to work with Azure ML from ADB. We are going to run a sort of setup statement here. So we want to basically connect now to ADB. So what we have to do is we have to mask that here. Essentially, you have to basically import your tenant ID. You can also use a secure way to do that without exposing that within your script. I did it relatively light, and within my initial run, exposed basically my tenant ID. You connect it to a workspace. The workspace you need basically to connect your experiment and your experiment name in AML, and this is the workspace of AML. So essentially down here in this particular experiment step, you connect to this instance, and then you get a login requirement where you log in with the code and you're then fully connected. You get an output and you know you're connected within your individual environment. I had a typo in here. This should be 22. So in case anybody caught that. So once we are connected basically to our AML instance, which is this instance up here in my other tab, I'll go in there in a second. The first thing we are going to take care of is creating a compute cluster. So compute clusters, again, you have that rich variety I've shown you earlier, is going to be available and should be chosen based on your use case. If you run DNNs, please use GPU. If you're not running DNNs and a small series, please use a smaller compute cluster, just because it saves you basically Azure credits, and it is not required to have like this big compute cluster if you have only small amounts of data. So this is also like a boilerplate portion that checks basically if the compute cluster exists. If not, then build it. So we are basically building this particular compute cluster in AML. And once this is all set up, you're good to go. You can basically select your data and do whatever you want with your data, running it as an experiment on AML. So here, in this case, we're using energy demand data from New York City. The data looks the following. So you have a timestamp, you basically have a demand, and you have, I don't know what the precip stands for, but then you have the temperature essentially. And we want to forecast the demand. So this is our goal here. So we are breaking it down basically in this univariate time series. So you see the timestamp down here, and then the demand that is going up and down essentially. And we want to build off this time series a model, again, univariate. That's the goal here in this example. So first, what we're going to do is going to split our data in train and test and validation. I think we are skipping the validation step here, I believe, but we're splitting our data respectively into the two data sets needed here. And then we are moving basically into setting up our forecasting experiment. So for our forecasting experiment, we require a forecast period of 48 hours. In this case, hours is the unit our time column is measured in. So 48 is the requirement by the business. This can be a bit different, obviously, depending on the business use case. In case you work in energy demand forecasting, but in this use case, we just set it to 48. And within our training data, we are now within our training setup, we are setting up this AutoML config under the following hyperparameters. So first, we're defining our forecasting, our task, which is forecasting. So if you have regression or classification, you would basically change this to regression classification. In this case, it's forecasting. You define your primary metric. This is how basically your model is going to be judged on by accuracy. So in this case, we are choosing an NRMSE. We are blocking models. We don't want to run these models at this particular time. You can also remove this and run these models. That's fully up to you. We are defining basically how long the model is going to run, what type of training data we are going to use, our target column basically, which is in this case the demand. We are selecting our compute cluster, in this case the AML compute. I showed this in the beginning on those selected hyperparameters. If you want to run it on a Spark instance, you would need to define this here in this particular hyperparameter. We are enabling our cross-validation and so forth. So these are like relatively standard parameters that are needed. And we define our forecasting parameters that are defined up here, basically, which the frequency is hour. So you need to say what type of frequency you're going to forecast on that. Let me scroll up again, on that 48, essentially. So this is all what is needed, essentially. And then we are submitting our experiment here. And what's going to happen is in AML, you will then get this particular entry here for energy demand, and the model is going to run in here. So I believe it is this particular run. So you can go here on the models and you see basically the model suite that is ran. It is relatively small because I excluded a couple of models and I enabled basically that this particular experiment shouldn't run that long. Hence, you only see a very few model, and it's just going to show you basically how this experiment is executed. And you could basically say that based on this particular model run, maybe like exponential smoothing is the best model. You can dive into the individual metrics here that are going to be loaded and so forth and take the model apart under any of these headers up here. I'm not going to dive into this too deep. I want to continue with the demo itself, but this particular model would be a choice basically if you're deciding not to select the ensemble model. Within this particular example here, obviously you can further enhance the model itself. I'm going to skip this here, and you want to, let me scroll down here, you want to enable advanced training. So within Univariate time series, a very common technique is to basically enhance rolling features. That is a very standard method. And what we are going to do here is we are enabling these lag times essentially in our forecasting parameters, and AutoML is going to build these features for you. So you don't have to worry about that as well. And you see, I basically also removed those blocked algorithms, and we can enable another run. So what's going to happen in this particular use case, let me pick the most recent run here. You see, first off, you run way more models because we now said there's no restriction. These lagged windows are basically built in. You see that the accuracy metrics, I think the prior run, it was 0.05 or 0.06, is now cut in half because you have a more richer suite of features essentially. Plus, you choose different algorithms that be maybe more efficient essentially based on accuracy. And those will be now visible to you within the leaderboard. You see up here the preview for the code generation, the feature I've mentioned earlier. It's unfortunately not enabled for me, so I can't click on it currently as it is in preview. I would need to sign up for the preview to get this enabled, but you basically have now the richer suite available. Again, you can take this apart. I just want to show you the functionality here. I'm not going to go through all the tabs as mentioned. You can see the individual child runs as well. And you can see basically what type of accuracy metrics you have achieved. I'm not saying this is the best model. It is just to show you the solutioning use case. And this is really creating the connection between ADB and AML, relatively easy. You then can retrieve basically also like in code form, instead of looking at the UI, the best ran model under basically your best scoring metric and so forth that you have chosen. You can basically look into advanced results and really take this apart, compare your inference runs. I have not enabled inference for this particular use case, more for the many model, which is the next notebook we are looking at. But this is just to showcase you the connection itself. Now, let's look at the more complex use case, which is, I think, a little bit more interesting. Let's look at the many model use case. So with the many model use case, this refers to the accelerator. What we are doing here is, if you remember that architecture I just have shown you a second ago for many models in particular, first, we are going to set up our experiment in exactly the same way. So we have basically our libraries here that are needed for our use case. We are going to connect to our environment. This is always the same. This is copy and paste, basically. Essentially, we are selecting an experiment. This time we are calling it many models. And we're working in this use case with different data. So this is orange juice data. The actual orange juice data would build you close to 12,000 models. We are using a small data set, so we are only building 10 for the sake of time. And we are basically retrieving our orange juice data from our blob container. So this is all set up, nothing fancy, and has nothing to do with really building the model. We are dividing our data set into a training data set and in an inference data set that we basically need to run the model. And again, we select our compute target. You have seen this in the prior notebook. It is all standard. There is nothing out of the box here. This is reusable code. By the way, the code base is available under our Azure example, so you could literally go in there, copy that, use it for your own use case to increase your productivity on your initial business use case you may work on. And then now we are going into what's specific to many models. So for the many models example, we are setting up our AutoML settings a little different than as you have seen in the AutoML config before. We're defining basically our partitioning. So this is the columns basically that divide your data set into what granularity and how many models you have to build and have to run, essentially. You're defining similar type of settings though, but you now have this grain column names in here, which is the granularity I just mentioned. And then you basically use those hyperparameters and apply them to the many models trained parameters. So this will enable this many model run. So from a code writing perspective, it's relatively limited. There's not much magic to it because the underlying accelerator will handle most for you. So if you think about in a non-solution accelerator use case, you would have hundreds of lines of code basically to divide your model. You need iteration functions. You need to be able to scale on a cluster and a node and distribute basically that scale to the individual run. Here it's done for you. You don't need to do that. And all you basically need to apply is basically your partition columns, which are important, and basically your AutoML settings you define up here, which are similar to the AutoML config. This is really it. And then in the end, you build your training pipeline. It looks a little bit different, and you kick off your pipeline in an experiment submit again. And by the way, maybe I just skipped over this up here. This is where you basically define how you want to distribute your compute, basically process per node, when it should time out, basically how many nodes you want to use. So you have control over that in parameters before kicking it off. In AML then, let me just give you an example. This is the data set, by the way. I looked at this earlier for the orange sales. Let me pick the example. So you can go under experiments into many models. So this is the experiment we built into the training step. And you see it looks a little bit different. So you kind of like have a almost like a flow chart here that shows you where your data set comes from. So you can literally click on this and pull the data set up if you're interested. And this is now all interconnected in AML for you essentially. And you can, let's see, explore. You can look at the data set we're training on. So this is basically our cut down data set. It has 50 rows essentially. You have your partitioning step. So this is what divides the data based on your granularity we just talked about. And then we have our many models train run. So this step essentially is now dividing our data set based on our granularity, in this case 10 times in 10 individual models. And this particular panel over here should look familiar to you, to the prior screen we have seen on the Univariate model. You can look at your individual run here. You can look at the child runs. So these are the individual 10 models now. The data set has been split up into, and you can see based on each run what model has been selected to be the leader model. So in this case, you see a lot of voting ensemble models in there, but also profit, for example, a more exponential smoothing. If you say you don't want the voting ensemble models, you would need to specify that in a parameter, and you get other models in this use case, which is usually then the second leading model. But obviously these type of merge or ensemble models score relatively high. You can click on this. You can look particularly at the model run. I think it only shows you the latest run essentially in here. But you can basically take this particular model run apart respectively to the individual store or brand you're focusing on here for this particular use case and dive into the individual metrics. So within AML, basically it helps you to break it down on a use case basis. Let's go back to the actual pipeline. So this is the pipeline that ran. Just to repeat, so it's very clear, you click at the training step and you can basically take it apart here. You can look at the individual parameters you have enabled and so forth, and you can look in the individual 10 models you have built. Within AML, within ADB though, it is shown to you as an output basically here. So those are print statements from logs where you can see the individual runs basically that are happening. You can explore these logs within your individual run here basically, excuse me, and can basically take apart what happened within each step. So it's basically just a print that you see, and you will see an error that may appear on this side if needed. You can then, if you want to publish this pipeline, you can set up basically your inference step, basically, which is relatively similar to the training step. It will just require basically like a parameter that you call inference steps that I declare here, but the setup is relatively the same. This time, just you pick the selected models that you have prior trained and run it on an inference data set. I apologize, the column headers here are a little bit out of sync basically, but this is then the predicted column over here that you can see after we ran our inference. So again, please disregard the column headers, they don't align to the actual column. But if we go back to AML, essentially to our experiments that I have shown here before, so under many models, we can look at our inference steps. So it just builds for you a new pipeline in here. And you see the 3 steps again, right? The model partitioning is important to align basically the data that comes into the model you want to run inference on. And here in the end, you have basically your inference step, where now you obviously don't have child runs because you don't train anything, but it is displaying to you the actual step that ran to create the output data set, which you can like select here essentially. So this is the input, this is the output, which we are displaying as an output data set down here. And it tells you how many predictions ran based on my print statement essentially. And this is it. You can then take this data set, write it back to your target source. We saw that again in the architecture, our target source, I suggested 3 sources you can use in a batch scenario. If you have a near real-time scenario, you may want to distribute that differently. And then you can visualize it with a visualization tool of your choice. Lastly, just very quick, I mentioned the example, so you can go into our Azure Machine Learning Notebooks repository. You see basically many different examples here also for classification regression. There are many different use case examples. So the examples I have shown to you here are the energy demand. This is for Univariate, and the many models Accelerator, which is the forecasting many models. I also spoke about the hierarchical time series Accelerator. You can test that out here as well. And import basically these notebooks in your environment. In this case, we discussing ADB. Let's switch back to our presentation and close this session here. So what would be the next steps after you basically ran these individual models? There are 2 I would suggest. So first, make sure your models are always logged. You can use MLFlow for that, or in case you're running, you want to run on more larger distribution, for example, you can enable Hyperopt, which is something that comes with ADB. Those are 2, at least the first stop is highly recommended, especially you want to persist your models ongoingly within your environment. And second, in case you plan to operationalize or for your inference runs more, or you think about a higher degree of deployment, let's say you run DNNs, you can do this with your GPU resources that are provisioned to you in AML, and you would then enable AKS essentially for that application scalability you're seeking within your final application. In case, obviously, you're having a front-end report and you don't need that type of scalability within AKS, you can go the data warehouse type of way. You can write to a target and then just read basically with your application or with Power BI from that target. This would close the session at this point, this webinar. I'm happy to hang on and take a couple of questions